Okay, so what we're going to do is we're going to finish this. I will slide back this over. This will be a little distracting on the video, but I wanted to just remind you of where we were before. So I'm going to start by drawing the shear moment diagram for section AB, so I'll need to know all these things at A and at B. And you know what I like to do is I like to go ahead and rotate this so it looks kind of like a regular beam. So what I'm going to do is just kind of slide this out of the way and come over here and draw this thing in. So I would draw it something like this. It has a distributed load on the side, which now looks like it's acting down. And it has a value of 3 kips per foot. Now, so when I'm looking at A, well, can't hardly see it. There's no moment at A, so no moment here. I'm not worried about the axial force, so that would be the AY force, but I am interested in the AX force. And when we solved for AX, we found that it was negative 36, so actually AX is to the left, which ends up in this orientation is up. Everybody see that? Now what's happening here at B? Well, let me slide back up here and look at what I calculated at B. So at B, I found, this is on section BC, so I found the moment at B to be negative 216. So I drew this right-hand rule as positive, so that means at B it's actually, what, clockwise, which means on AB it would be counterclockwise. So it would be shaped like this. And that's a value of 216 kip feet. Now what about the reaction? Again, I want the x component. So I solved for bx here, and I found that bx was 0. So there is no shear at B. So that seems to be all the pieces that I need. So let's go ahead and extend our template, and let's draw the shear diagram. So this would be shear in units of kips. So what is the shear at, in this case, A? 36. Is that positive or negative? Positive. Now remember, our principles is that the change in shear is the area under the load diagram. So the change in shear from the left side at A to the right side at B, that's the change in shear, should be equal to the area in the load curve. What's the area in the load curve for the same distance? I forgot to enter the length. Well, it's a rectangle, so base times height, 12 times 3 is 36, and that's negative, so 36 minus 36 is 0. That's good, because we knew the shear here was 0. And also we know that the slope of the shear diagram is equal to the load. And the load is constant, so we have a constant slope, and it's negative. So there's our shear diagram. Any questions about that? So now we'll look at the moment diagram. So here's our positive moment, positive x. We'll have units of kips per force, and length will be feet. Do we know the moment anywhere? What's the moment at A? Yeah, it's a pin, so it's 0. What's the moment at B? Oh, sorry, what's the bending moment at B? It's 216, and it's what? Positive or negative? Positive. So hopefully I'll hit that. We know for moment that the change in moment is the area under the shear diagram. So the change in moment from A to B looks like it's positive 216. Is that also what's under the shear diagram? Well, the shear diagram would be, looks like it's a rectangle, so it's 1/2 base, which is 12 feet, times height, which is 36. Hopefully that's 216. Is it? That'd be 18 times 12. What's 18 times 12? Positive 216? So that's cool. And then the slope of the moment diagram, we know, is equal to the shear. So the shear starts off at a large positive slope and decreases to 0. So a parabolic curve or a quadratic curve, it looks like that. So there's my shear, there's my moment diagram. Any questions about that? So that was, I forgot to label this. This would be section AB. So let's come down here and do section BC. Now BC looks just like a beam, so there's no kind of rotation involved. I'll just draw it in. So it has a load right in the middle. That's 15 kips. And 4 feet and 4 feet. What do we know is happening at B? Well, let's refresh ourselves. Remember that we solved this section. So the shear at B would be given by By, and By is 19.5, but it's not. It's negative, so it's down. Right? So that means I have, this is down 19.5 kips. And over here at C, we solved for that, we found that it was 34.5 acting up. That takes care of the shears. What about the moments? Well, what's the moment at B? It was negative 216, so it's going to be opposite that, right? So it's going to be like this. And what's the moment at C? We solved for that, it was 0. So this transferred all that data over. So now I can extend the template, left side, right side, and let's, oh, and also we got this load here in the middle. That's going to give us another point to change. I'm going to have to wedge it in here. Sorry about this. Make it fit. So there's our positive shear, positive X units of kips. So what is the shear at A? Yeah, it's negative 19. What's the shear at B? Negative 34. So according to our relationship, the change in shear is the area in the load diagram. So what's the change in shear over the first 4 feet? Be the area in the load diagram of the first 4 feet, which is nothing, 0. So it should be no change. And the slope of that curve is given by the load, and the load is 0. So 0 slope, horizontal line. Now as we go from the left side to the right side and pass under this 15 kip force, it changes our shear by how much? 15, negative 15. So that comes out to be negative 34.5. And now we know that it should be that on the same. So hopefully the change in shear here is 0, and that's given by the area of the load curve, which is also 0, so that worked out great. Also, the slope is given by the load. Load is 0, so we have 0 slope. So we've got this kind of stair-step looking shear diagram. Okay. I don't think I'm going to have room to squeeze the moment diagram over here, so I'm just going to draw it off here to the side. If that's okay. So I'm going to redraw it this way. So I'll still have my length and the piece right in the middle. And what do I know about my moment? Well, my moment starts off at 216. Is that positive or negative? Positive. So it's going to start off at 216. And do I know the moment at C? Yeah, it's 0. So over the first 4 feet, I know the change in moments to area of the shear diagram. What's the area in this part of the shear diagram? Well, it's a rectangle, base times height. So that's 19.5 times 4. What is that?
78.
78. So what's 216 minus 78?
138.
138? So that's the change. And then the slope of the moment diagram is the shear. The shear is constant and negative. So there's a constant negative slope. Actually, the value would be 19.5. And then the change in moment over the last 4 feet is given by the area of the shear diagram in the same section. That would be this value, 34.5 times 4. Hopefully that's 138. So that brings us to 0. That checks. And then the slope of the moment diagram is the shear, and the shear is constant. So we have a constant slope and much steeper, negative 34.5. So there's my moment diagram.
When you first found your moment at B or C, did you assume it was positive or negative?
That's a good question. I'll have to slide this back over and see. I did not assume bending moment sign convention. I just assumed right-hand rule. So for example, when I started here at CD, I did right-hand rule for my moment and found it was 0. When I went here to B, I did the same thing and found it was negative. So I just know it was opposite that. So in terms of sign convention for bending moment, I actually assumed a negative bending moment here. And since I got a negative value, it's a positive bending moment.
So when you just drew it as right-hand rule?
I didn't want to try it because it's much more difficult to decide what's positive bending moment on these other pieces. I just decided to go to right-hand rule all the way through and then correct it when I drew the diagrams in this way, where I'm assuming compression's on the top.
So you drew, even though your number was negative, you drew it as positive there.
Well, that's the right orientation.
Gotcha.
Remember, I assumed right-hand rule and it was negative, so it's the other way.
Because it came out negative.
Right. So when I draw it this way, now I'm looking at it, and the way we're drawing the values, that's a positive bending moment. Yeah.
So what did I remember you saying something about which way you look? It depends on which way you look at it. What's positive bending moment? So
what I want to do to make it easy on all of us is when you draw it like this, we're just always going to assume when you turn that edge over like that, then this is going to be a positive bending moment. Up until that point, don't worry about it till you actually get to drawing the diagram. We're just going to assume that when you draw it, the compression is going to be on the top and the tension is going to be on the bottom, and not have to worry about trying to keep track of that. You've got other things to worry about. I think are a little more important than just the sign convention. So, any other questions about this? I think this is a pretty decent problem for the test. All right.